Hi, welcome back.
Hello.
Hi. Hello. So we're starting to leave some shapes behind. We did quadrilaterals, we did those parallelograms and squares and rectangles and trapezoids and kites. Last chapter we started in on similar figures and we did a bunch of proportions, fractions equal fractions, and it basically turned into a bunch of cross multiply and solve. This chapter, chapter 8, is all about right triangles. So we're going to figure out different pieces of right triangles. We're going to look at the Pythagorean theorem a bit more closely. I'm going to give you a shortcut to some Pythagorean triangles. I'm going to give you a shortcut for other right triangles in general, so that way you don't have to use the Pythagorean theorem, because I know you don't like using it. It's a lot of work. So I'll give you some shortcuts. That's coming up soon. To start that, we're going to start with geometric mean. Okay? The geometric mean between two numbers is the square root of whatever you get when you multiply them. Okay? So the geometric mean of two numbers, we'll call them A and B, is whatever we get when we multiply A and B and then take the square root. Okay? That's the formula for geometric mean. This one here. All right? Let's scoot down to the examples 1 through 6 and let's play with these a little bit so that way we can figure out how these formulas work. Okay? I'm going to start with number 6. YOLO. All right, I want the geometric mean between 4 and 25. So the geometric mean is the square root of whatever I get when I multiply one of the numbers times the other. 4 times 25. 4 times 25 is? It's 100. And the square root of 100 is? Yeah. That's it. Yo, that's it. That's all there is to it. That's it. That's it. Let's look at number 3. Because number 3 has one tiny little step more, but it's basically the exact same thing. Ready? All right. So I want the geometric mean between this number 6 and this number 9. The geometric mean is the square root of whatever I get when I multiply them together. 6 times 9 is 54. And I don't want decimals. That's rounding. I want the exact number, which means I need an answer that still has a square root in it. Exactly. I don't have a whole number that I can multiply to itself and give me 54. So what I'm going to do is I'm going to look at this pair of factors, these two numbers that we multiply together to give me 54. Now I'm going to break the square roots at the multiplication. So now I'm looking at square root 6 and square root 9. Does square root 6 have a whole number square root? Yes. 3 times 3 is not 6. 3 plus 3 is 6. 3 times 3 is not 6. So I have this. 3 times 3 is 9, and so 9 has the whole number square root. But that answer looks really weird, doesn't it? Yeah. Square root times 3. We usually like writing it in the other order. So I can switch the order on this and write 3 square root of 6.
Do we have to?
Yes. All right? Not too hard. Good. I'd like to look at number 5. That's it. This one right here. Not this one. This one. Okay? Let's look at number 5, please. So I have 12 and 20. The geometric mean between 12 and 20 is the square root of 12 times 20. Now, I could multiply these together and get a really big number. But I don't want to. And my directions also don't say round to the nearest whatever, which means I can't put this into a calculator and get a decimal because I want an exact number when it doesn't tell me to round it. So what I'm going to do is I'm going to think of 12 as something times something, where one of the somethings I know the square root of. Give me two numbers that multiply together to give me 12.
6.
2 what? 3 times 4. 6 times 2 also works. But 6 doesn't have a whole number square root. 2 doesn't have a whole number square root. So while you're not wrong, it's not helpful. But 3 times 4, Edward, put the phone up, please. Put the phone up, please. Thank you. But 3 times 4 is helpful because 4 has a whole number square root. Can I do the same thing with 20? Okay, give me some factors for 20. 5 and 4. Again, because I know the square root of 4. All right, so I'm going to bring the square roots of 4 out here in the front. There's one of the square roots of 4. There's the other square root of 4. And then I'm going to put the square root of 3 and the square root of 5 together in its own little casita because I don't have a whole number square root for those things. Are we okay with what I did? Yes? 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 Okay. What's the square root of 4? 2. Oh, wait, what's 3 times 5?
13.
But what's 2 times 2?
4.
And so there's my final answer. Okay? Do y'all want to see number 4 because there's a fraction in there?
Yep.
Yes? All right, so scooting over to look at number 4. I want the geometric mean between half and 2. The geometric mean is the square root of half times 2. Now what's half times 2?
1.
How'd you get that? Okay. But if I didn't have a calculator? If I decided to get mean and say no calculator for this test?
No, multiply by 0.5.
All right, you could multiply 2 by 1.5. Here's how I want you to think about it because this sets you up for algebra 2. And that's what's next. Yeah, I'm going to take the 2 and I'm going to put a 1 under it to turn it into a fraction also. Because the way to multiply fractions is straight across. Cross multiplication is when there's an equal sign between them. So this is the same as 2 over 2, which as she was saying, you cancel the 2's out and it becomes a 1.
Oh, I just put 1/2 and the square root of that 2.
Yeah, and all you do is cancel 2 and 2. Yeah, there you go.
Wait, you're going to use calculator in algebra 1?
In algebra 2? Very rarely. Not much calculator work in my course. What's the square root of 1? 1, because 1 times 1 is 1. That leaves you number 1 and number 2 to work out on your own. Okay? All right. I'm going to zoom back up to this theorem. Because this theorem is going to set us up for the 2 shortcuts I have for you. That's going to make things like super, super easy. Thank you very much. All right. It says, if an altitude is drawn to the hypotenuse of a right triangle. All right. So we're going to look here. Do I have a big right triangle right here? Yes. Here is the hypotenuse because this is the right angle for the big right triangle. This is the altitude because I have a right angle forming right there at the hypotenuse. Yes? Okay. Let's throw that highlighter away instead. When I have this set up, then this triangle, which is the one that's formed here on this side, the medium one, I'm going to color it in yellow for you. So this triangle is similar to the big triangle. And this triangle is also similar to the big triangle. Let's write those similarity statements, because the challenge is trying to figure out which parts correspond to which other parts. Okay? Can you please name for me the large triangle? Give me one of his names. ABC. Isosceles would be a classification. That's what kind of triangle he is. So it would be like high school student for you instead of Ethan. Okay? I want name, not what thing he is. Okay. So now I said that this yellow triangle is similar to this big multicolored triangle. So I'm going to try to find a way to write the name of this triangle so it's in the same order as this triangle's name. One more time. Why does this one have a C instead of a B? A D instead of a B? Because we're looking at this triangle right here. Whereas the big triangle is looking at this one. Okay. All right. So in the big triangle, C is the angle that holds the right angle. Yes? In this triangle, which angle holds the right angle?
D.
D. That means that C and D correspond. Now B. In the big triangle, if I move from C to B, I am on the shortest leg of this right triangle. Do you see it? Okay. So then I want this letter to be the letter going along the shortest leg of this triangle. So C. Which makes my remaining letter right here, A. Okay? Now we need to do the same thing over here. So I have triangle. I need to put letter, letter, letter. All right. And I want to match it up with this. All right. C was next to the right angle. Which letter here is next to the right angle? D. B is from the right angle along the shortest side. So from the right angle to the shortest side, you get to? That's the order those names need to be in, so I know which pieces correspond to which other piece. This is really the hardest part about the section. It's figuring this out. I'm going to strongly encourage you that when you get triangles that have letters, and I'm going to look at the assignment really quickly. On the assignment 7 and 8, you have to write similarity statements, identifying the triangles. You got to do this. Okay? So you got to match them up. All right? 7 and 8, I think, are the only ones that you need to practice on. Okay? On the homework assignment. Questions on this? All right. Let's go into the shortcuts on calculating things. I have two shortcuts for you. The first one says the geometric mean altitude. That is an altitude that's drawn to the hypotenuse of a right triangle. So here's a right triangle. Here's the right angle. That makes this the hypotenuse. Here is the altitude of that triangle. This altitude is separating my hypotenuse into two different pieces. Okay? The altitude is given by the geometric mean between the lengths of these two segments. Let me go into the diagram. let's use the colors and let's write this formula, okay, to make sure that it's sticking properly. Okay, the altitude of this right triangle is the geometric mean of the two sides of the hypotenuse. They got created by that altitude. Okay? Flip back to the front page. Join me on the very first triangle for us to calculate. And let's use this formula to calculate those measures. Okay? We're looking at number 7. Do I have a big right triangle?
Yes.
Yes, here's the right angle, so here is the hypotenuse. That makes this the altitude, and these are the two pieces that the hypotenuse got cut into by the altitude. The measure of the altitude is the geometric mean of the two pieces of the hypotenuse. X equals square root 3, and the directions say to the nearest hundredth. I get to now put this in my calculator and get out a decimal. Go for it. 1.5? Double check it. Do square root 3.
1.7.
1.7. That's it. That's it. We're done. That's the answer. Easy enough?
What is it? That's to be
It means almost equal to. Yeah, he's talking about these squiggly equals. That means más o menos. Approximately equal to. All right. Do you want to do 8, 9, or 10?
10.
10. All right, number 10. Do I have a big right triangle?
Yes.
Yes, there's the right angle. That makes this the hypotenuse. Here is the altitude, and it is equal to the two pieces of the hypotenuse multiplied together, and then we take the square root of it. Okay? So, the altitude is the geometric mean of each piece of the hypotenuse. Don't need it. Her question was, what about the square root of 12? My answer is, I don't need it right now. Has nothing to do with that side right now. All right, going to simplify this down. Nothing to do on this side. Square root 3 equals, do I need to write times 1? No. All right, if on one side I have square root 3, and on the other side I have square root of, I don't know. What is that? I don't know. Both sides have square root, right? And that's the only thing they have? I can get rid of the square root. Yes, no. That's it. I'm done. Look, I found y. I don't know what x is, but we'll get to that part. Easy enough? Do you want one more example of this, or shall I go on to the next thing?
Okay.
Do you need another example of this, or should I go to the next thing? Next thing? Here's your next shortcut. Next shortcut says geometric leg theorem. The leg they're talking about is in our right triangle. We have the side that is the hypotenuse. The leg is any other side. Okay? All right. if I have an altitude drawn to the hypotenuse of a right triangle, so here's that setup again, it separates the hypotenuse into two pieces. The length of the leg of this right triangle is the geometric mean between the length of the hypotenuse and the piece of the hypotenuse that's closest to the leg that we're looking at. Okay, let's look at it more closely with the picture. This theorem says the length of the leg is the geometric mean of the entire hypotenuse, all of it, the whole thing, times just the piece of the hypotenuse that is the closest to the leg that we're looking at. All right, let's go back to those examples, the one that we started but we didn't know what y or x, or there was a letter there that we still wanted to find. Let's go back to that one, okay? So we're looking at number 10. Okay, I found what y is. Got that. I'm now trying to figure out what's x. The geometric mean leg theorem says the measure of that leg is the geometric mean of the entire hypotenuse. What's the measure of the entire hypotenuse? Plus 1. The whole thing. It's 4. Thank you. Times just the piece of the hypotenuse that's closest to the leg that we're interested in. So 1. So the leg is equal to the square root of 4. What's the square root of 4? And we're done. That's it. That's all. We didn't even use square root of 12 at all. We didn't use it. Extra information that we did not need for this one. Do you guys want another example of this, start to finish? I've got some people shaking heads. You're feeling comfortable with it? I'm just checking around the room. I've got some nods that you're feeling comfortable. More nods, you feeling okay with it? Yeah. My Ethans, are you feeling okay with this? I mean, you're giggling, so I assume you are, but I want to check. You feeling okay with it? And then here, my middle row. Yes? All right. And then down front. Yes? Yes. All right. Thank you very much.